Hi everyone, I hope everyone is doing okay. This is our fifth video. So remember from last time that we defined the notion of the Galois group. So if you have K over F, field extension, we define the Galois group of K over F to be a set of automorphisms of K which fix F, so which act trivially on F. And then we calculated some Galois groups, some easy Galois groups. Now, before we proceed, let's make an observation here. So note, okay, so let's say sigma, suppose sigma is an element of the Galois group of K over F. Okay, so what does that mean? That means that sigma goes from K to K and fixes F. So for every A in F, you have sigma of A is equal to A itself. Okay, so now let me take A in F and alpha in K. Okay, so then what's sigma of A alpha? Sigma of A alpha, well, sigma is a homomorphism, so this is sigma of A, sigma of alpha. But now because A is in F, sigma of A is just A itself. This is A sigma of alpha. Okay, well, of course, if I take alpha and beta in K, sigma of alpha plus beta is sigma of alpha plus sigma of beta. Sigma is a ring homomorphism. So think about these two conditions here. Does that remind us of anything? What does that tell us about sigma? So sigma respects addition, and sigma of A alpha for any alpha in K and A in F is A times sigma of alpha. Exactly. These two tell us that sigma is an F linear map. So think of K as a vector space over F. Well, so that's a vector space over F, that's a vector space over F. This tells us that sigma is a map of F vector spaces, of vector spaces over F. So sigma is an F linear map. Right? So map of vector spaces over F. Okay, so every element of the Galois group, you can think of it. Let me make sure that we don't lose the camera. Sorry. So every element of the Galois group of K over F is an automorphism of K, which is F linear, which is a map of vector space. Yeah? Well, the converse is also true. Now suppose sigma from K to K is an automorphism which is K linear, which is, F linear. Okay, so then what does that mean? Well, let's consider, okay, so let A be in F, and now let's consider sigma of A. Well, this is equal to sigma of A times 1, and now sigma is F linear, and A is in F, so by F linearity, this is A sigma of 1, right? This is by F linearity. And then well, sigma of 1 is 1, so this is just A. So sigma of A is just A. the conclusion is that, so what's the conclusion here? The conclusion is that the Galois group of K over F, you can think of it as the set of automorphisms of K, which are maps of F vector spaces, of vector spaces over F. You can think of it as automorphisms of K. So let me erase this and write down what the conclusion is. The conclusion is the Galois group of L of K over F is equal to the set of automorphisms of K, automorphisms of K, the condition that which fix F, that translates to, you can equivalently phrase that as, which are F linear. Yeah, the Galois group of K over F is still automorphisms of K, which are F linear. This condition fixing F is exactly equivalent to being F linear. Okay, so that was a remark that I wanted to make before we continue. Okay, now the camera again, sorry. Okay, good. Okay, now, okay, so let K over F be a field extension. An arbitrary field extension, sigma, an element of the Galois group. Let's take a polynomial F with coefficients in X. Okay, so this is our setup. Now, if alpha in K is a root of F, then F of sigma of alpha is equal to so if let's say F is equal to some AI x to the power of I, this is F of X, these AIs are in F, right? So now F of sigma of alpha, this is equal to, so this is now the sum AI sigma of alpha to the power of I. But these coefficients, these AIs are in F. Polynomials coefficients. These guys are in F. So AI is the same as sigma of AI. Remember sigma is the of Galois group of K over F. It fixes F. So this is the same as some sigma AI, sigma alpha to the power of I. Okay, and now this is equal to, well, sigma is a ring homomorphism, so you can factor the sigma out. This is the sigma of some AI alpha I. It's sigma of F of alpha. Well, F of alpha is 0, so this is sigma of 0. It's equal to 0. So what's the conclusion? See, we start with the polynomial F with coefficients in F. a root of that polynomial, an element of k which is the root of that polynomial, and applied an element of the Galois group of k over f to that root. And we saw that the outcome, so sigma of alpha, is again a root of f. F of that is equal to 0.